I've built a 32-bit floating point converter in Excel VBA, so it converts both ways. We can go from floating point binary to decimal, and we can also go from decimal to floating point binary. So let's just give an example here. We're going to start in this box here, so we can put in any decimal number you like. So let's say we put in 17.125, and you can see the numbers changing automatically as we put them in. So this row here is the floating point binary representation of this decimal number that you put in this box. And you can see, as I said, it changes live, so it's quite handy to be able to see it changing as you change each digit. We've got the sign bit up here. We've got the 8 bits for the exponent and the other 23 bits here for the mantissa, or if you prefer to call it the significand. We've also got 3 bits here at the end here in red, and we're using these for doing the rounding. So we've got a guard bit, we've got a rounding bit, and we've also got a sticky bit. Now the sticky bit's actually 8 bits which get ordered together to give us a value, but we'll get into that more detail at the end of the video. So let's put in a few examples here and we can see how useful this is going to be. So we can clear this off, and we can notice that whenever we put examples in, that we can put them in another format. So we could put in a format, say 1 e to the power of, say, 32, and it will get in this scientific format, which is quite handy, and that's minus 33, and it changes automatically. And of course you can just clear off the values that you've used. So that's the decimal to floating point conversion tool. Another thing I've noted here, it tells you what the number type is. So for example, this one here is a normal number, but we can also put numbers in which are going to be subnormal numbers. So say you put the point 0.1, and then we run this through with a lot of zeros. Eventually, when your number becomes so small, it will go from a normal to a subnormal number, and if we continue doing this, it will just head off and it will underflow to a value of 0. Now we can do the same the other way. If you put in a large number, then you can see it's a normal number, and eventually it will just overflow to infinity. So there you see overflow to plus infinity, and it will also overflow to minus infinity as well. So it covers the full range then of the 32-bit floating point numbers. So let's look at above here. Now this one is doing the opposite. It's going from floating point binary to a decimal value, and we do that by changing the values here in this 32-bit number at the top. So I can change each of these individually, and as I change them, you'll see that the number in this box changes, and this is the decimal representation of this 32-bit floating point number. And again, it's got it in a value here, which is going to be the hex value, and it will tell you whether the number is going to be a normal number or a subnormal, or whether there's an underflow to 0 or an overflow to infinity. Now it's quite handy in here in order to look and see the number representations just by changing these values. So for example, if you were looking to look at the smallest number that you can represent in floating point as a single precision 32-bit floating point binary, it will be this number here. So with that one pressed, this is the smallest number you're going to be able to represent. And you can see that here. If I was to Control C and I was to paste it in here, again you get the same number. Now if I make this number any smaller, it's just going to underflow to 0. So if I make that minus 46, and you can see here it's actually underflowed to 0. So let us work our way up the number system. We've seen that this is the smallest 32-bit single precision floating point number that we can represent, and we see it's a subnormal number, and we can see the value in hex for that number. So let's look at the largest subnormal number that we can represent here in our single precision. So that's going to be all ones in the mantissa. So that value there is the largest subnormal number that we can represent, and if we go any higher it will change from subnormal numbers to normal numbers, and you can see that number in hex here as well. So now let's look at the smallest normal number that we can represent, and that's all going to be all zeros, and there has to be 1 in the exponent in order to make it a normal number. So that's that one there. So this is the smallest normal number that we can represent in a single precision 32-bit floating point. So let's work our way up and we'll find the largest number that we can represent. So the largest floating point number that we can represent are all ones here, and a 0 for that last one, and all of the mantissa bits are going to be a value of 1. So this here is the largest floating point number that we can represent, and this is the value for it in hex, and of course it's a normal number. And again, you can take this here and you can place it down in here and you'll get exactly the same number. So let's go ahead and we'll look at the next part of this, which is the error in the approximation. So let's first of all clear everything off, and we'll start back at a clear screen. So let's put the number pi in. It's going to be 3.14159.265.359. So that's the first few decimal places of pi, and we can see that it's generated this number here, and this is the hex number for it, and it's a normal number. So let's go ahead and we'll see what the floating point binary representation of that actually gives us. So if we were to repeat this here, so we make that a 1, a 1, a 1, a 1, and we'll build up our value for pi. We can see here that the value for pi is actually going to be this value here, 3.14159.274, and so on. So let's see what's happening here, because these two numbers are different. Well, if you look at the bottom number, you'll notice that if I was to take away this value of 9, there's no change here in this floating point number. I'll put it back in just to show you again. So that means that this number is pi. If I take that 9 away, well, that number is pi as well. I could take the 5 away. That number is pi as well. I could take the 3 away. That number is pi. Let's try taking the 5 away. Well, there's a change here, so that's not a value of pi. So we can put our value for 5 back in, and we can see that we'll go back to this value here. So the value for pi is only going to be accurate to a certain number of significant figures. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 significant figures, but it's going to be 1, 2, 3, 4, 5, 6, 7, 8 decimal places. But whenever we put that number in here, we actually get a number that's different here. So this is the actual number that we're going to get stored. So let's take this number here and we'll just stick it down in here. So whenever we stick it down there, again, this is just going to be exactly the same. So whenever we start taking these away, you'll see again that the number doesn't change until you get down to the value here of 7. So everything's exactly the same. As soon as I take that 7 away, it's a different number. So we put that 7 back in. And notice if we were to make that, say, 7.1, there's no change, or 7.2, or 7.3, or 7.4, or 5, or 6. You see that there's no change. So this here is the actual representation pi in 32-bit single precision floating point numbers. It doesn't get any more accurate than that, and it's actually been rounded. The value we put in was a value of 9265, and it's rounded the 65 up to a 7. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 significant figures, and we've got 1, 2, 3, 4, 5, 6, 7 decimal places. So we can represent pi in 32-bit single precision floating point numbers to only 8 significant figures, or 7 decimal places. So let's have a look and we'll see how that rounding occurs. And we've got the rounding bits here. So the number for pi that we started off with was actually 265. So the question is then, how do we go from the 65 to the 7? Now we could have a look at that and said, well, if 5's in the middle, we automatically go up, or 5's in the middle, we automatically go down. But that's not what we do. We use something called nearest neighbour rounding, and this is going to be given by these 3 bits here. So the first bit is going to be called the guard bit, and the round bit, and the next bit is called the sticky bit. So what we want to do is work out what's happening after the value here of 5, and we can actually do that because these extra bits here in effect are going to give us extra values in the mantissa. So we're going to have one value here, we're going to have another value here. Now this sticky bit isn't actually just one value. I've actually used the next 8 values in the mantissa. And what we do is we OR together the next 8 values in the mantissa, and if any one of them is high, then we get a value of 1. But if all of them are low, we get a value of 0. Now the guard bit here has got a value of 1. So if any of the rest of the bits, which are the rounding bit and the sticky bits, have got a value of 1, then we pass this 1 over to the left and it ripples up through. And in the case then, what in effect happens is we round it up to the next nearest value. So the next nearest value is going to be rounding up, and it's going to be rounding up from 65 to the value of 7. And that's the reason why this number here, 3.1415927, is the 32-bit single precision floating point value for pi. So now that we've got some understanding of that, let's clear this off and then we'll have a look at the error in our approximation. So again, we can put our value in for pi, 3.14159265359, and we can put our values in here. So this is our actual value that's going to be held as a floating point number when it's converted back to decimal. And what we can do is we can just take one value away from the other. So if we take one value away from the other, we're going to get an error in approximation, and that's our error there, and it's a small error, e to the minus 8. So that's all there is for this video. I'm going to extend on this tool and I'm going to produce a floating point addition, subtraction, multiplication and division, and we can use this here in order to help us build our floating point unit. So thank you for listening. I'll get you on the next video. Goodbye.